SwayamPrabha. Digital India. Educated India.
Now let's design a PID control system for the aircraft attitude control problem in frequency domain. PID control design for aircraft attitude control in frequency domain. First, we'll set the problem, then we'll solve the design of PID control in frequency domain. Example, the aircraft attitude equation in one axis can be written as I y double dot equal to u plus disturbance acting on the system. So here I is assumed to be 1 kg meter square. U is the control input. MD is the disturbance. Now design the PID control in such a way that satisfy the following specification. The following specification basically the mission objective of the problem. So first specification is rise time constraint, which is TR less than 30 seconds. The system should reach to the desired value within 30 seconds, and a maximum overshoot constraint assumed to be less than 30%, and settling time constraint TS should be less than 100 seconds. So system should go to steady state value within 100 seconds. And another condition or the constraint should be followed. The steady state error for a step disturbance MD must be 0. And now let's start solving the problem. Solution. So we'll be designing the control system in frequency domain, and the aircraft attitude motion in Laplace domain, we can write GP of S equal to 1 upon S square. This is basically Planck transfer function. This is already you have derived in the previous lectures. Not in previous, in the, while we are talking about the equation of motion of the aircraft, we have found the equation. Now we'll be designing the PID control, how we can come up with the combination of PD and PI. Let's look. A PID control can be designed as a combined PD and PI controllers. Let's consider the PI and PD are in the following form. PD controller can be written as in the form of GC, basically the controller transfer function, and PD controller. We're writing in this form KPD TPD is plus 1. So in this form, we are writing the PD controller. Basically, we can write, if you look carefully, it is basically PD controller. We can write GCPD equal to, we can write KP E plus KD E dot. Or we can, in Laplace domain, we can write GCPD is KP ES plus KD is ES. And if you'd like to simplify further, we can take KP common from both sides. It will be E of S plus KD by KP S ES. And if you denote KP here as a KPD and KD by KP as time constant by TPD, so we can write the above expression KPD 1 plus TPD is into ES. And if you would like to write the transfer function, okay, this is a mistake here. This is basically controller. We can write this is a controller, and this is, for example, E of S is the Laplace domain. So we can write from this E of S by E of S, we can write KPD into 1 plus TPD and S. So this is the transfer function for the PD controller, and we can denote by GCPD. So this is how we can write in simplified form as here. Now let's consider similar way. You can consider API controller as in the form GC PI equal to KPI into TPI, the time constant, S plus 1 divided by S. So similar way you can proceed and we can find this structure. Now if you combine this PID controller, the combined PID controller can write GC, the overall control system or controller. For controller transfer function, we can write K into TPD S plus 1 and TPI S plus 1 divided by S. And from this, we can write K into TPD plus TPI plus S into TPD TPI plus TYS we can write. And if we further simplify, we can write KP plus SKD plus KIS. This is basically PID control, structure of PID control. So here we can write where the proportional derivative and integral gains are, we can write Kp equal to K into TPD plus TPI and Kd equal to, can write K into TPD, TPI and K equal to K. So this is how we can design the controller gain of the PID controller. Now we'll find how we can design the PID controller in frequency domain. We'll start. First, let's look at the overshoot and phase merging, how they are related. Let's look that figure. Let's consider the following figure, which relates between phase margin in degree and maximum overshoot in percentage. This already you have done in the before the few lectures. So here, let's assume this is maximum overshoot axis, MP percentage, and this is phase margin in degree. So we'll start. So this is the different points. This is 10 degree, 20 degree, sorry, 10%, 20%, 30%, 40%, 50%, 60, 70, 80, 90, and 100. And the phase margin in degree, wait, let's assume this is 10, 20, 30, 40, 50, 60, 70, and 80. And the relation between these we can come up with like this. Something like this. And since we are given the overshoot, we are given, which is basically 30%. For the 30% overshoot, let's assume this is the 30% overshoot. Actually, this plot should be a little different. Let me redraw the figure again. Something like this. So for 30% overshoot, we can assume this is our phase margin. So from the figure, for 30% overshoot MP, phase margin is assumed to be phase margin P is greater than 38 degree. We are assuming this value. For this plot, we are getting this value. And for the safe side, let's increase this phase margin a little higher. So to give ourselves some margin, let us choose phase margin equal to 45 degree. So in the safe side, we are assuming this value. Now we'll find the value of damping ratio for the given phase margin. So we can again refer the relation between the phase margin and damping ratio plot. The relation, why I need to find the damping ratio? Because we're going to find the gain cost over frequency. And there is a relation between the gain cost over frequency and rise time, settling time. And in those relations, we had this damping ratio factor, if you notice, because we have already derived those expression. The relation between damping ratio and phase margin in degree, you can have the plot. This is phase margin in degree, and let's divide the y-axis. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And damping ratio are in the y-axis. This is, sorry, x-axis. This is damping ratio. And 2, 10, 0.2, 0.4, 0.5. Sorry, let me write 2, 10. 0.2, 0.4, 0.6, 0.8, and 1. And the varies like the damping is the maximum portion, sorry, the phase margin varies with respect to damping ratio. We have the plot. Something like this. Yeah. And for the given phase margin, 45 degree, this is 45 degree. At 45 degree, we're assuming so we are assuming the 45 degree. So some value here and there it's fine. If it is plus minus 0 point something, that is okay. So for 45 degree, phase margin, the damping ratio is found to be 0.42. We are assuming this value. So it is just in this range, it may be 0.41 or 43. So we are taking this range value 0.42. Now let's find the gain cost over frequency from the relation between the rise time and gain cost over frequency, and rise time, settling time, and gain cost over frequency. So let's assume the following relation, which relates the omega z and rise time tr. So we have omega z greater than pi minus beta. This already you have found tr 1 minus zeta squared and put over 4 zeta to the 4 plus 1, this is zeta, and minus 2 zeta square. So this is the relation between the gain cost over frequency and rise time. Now, substituting the value of zeta equal to 0.42 and tr rise time. Sorry, this is the relation between the gain cost over frequency and rise time, and tr equal to 32nd. Omega z is found to be greater than equal to 0.0875 radian per second. Now we'll find again the gain cost over frequency from the relation between the gain cost over frequency and settling time. Let's consider the following relation, which relates the omega z and settling time ts. So we have the relation omega z greater than equal to natural logarithm 0.02 1 minus zeta square and divide by zeta ts for zeta to the 4 plus 1 minus 2 zeta square whole root. And substituting the values, substituting the values of zeta equal to 0.42 and ts equal to 100, omega g is found to be greater than equal to 0.1135 radian per second. Let's put some margin because we are getting the two different values for omega g. So to give some margin, let us choose omega z equal to 0.12 radian per second. Because if you notice, it's all are greater than, because it is greater than actually that values, it is also greater than that value. So from these two conditions, we are choosing this gain crossover frequency. Now we'll move how to design the PID controller. Let us write the controller in the following form. Where GC is equal to K GPDS and GPIS. This is already have done. So we are writing in this structure, and the open loop transfer function. This is basically the controller part, controller transfer function. And open for the unity feedback system, we know for unity feedback system, the open loop transfer function, you can write G naught of A is equal to GC S and GPS. So HS is assumed to be 1 for unity feedback system. Now if you substitute GC from the previous equation, you can write K G PDS, GPIS, and GPS, the plant transfer function. So here this is basically plant transfer function. Now we'll design first PID controller. So as you know, PD controller basically add the phase to the system. So let's assume the PD controller adding 5-degree phase okay. First we'll assume, let's assume the first PI controller. So PI controller basically gives the phase lag and PD controller phase lead. So let's assume the PI controller giving the phase 5-degree phase lag at the desired gain crossover frequency omega g. So that is, we can write GPI is GPI of JPG at gain crossover frequency is giving minus 5-degree to the system. Now the phase margin we can write PMP equal to 180-degree plus G naught J omega G. This is already how to find the phase margin at the gain crossover frequency. So we can write 180-degree, and for this part we can write plus GP the plant, because we have PI controller, PD controller, and gain does not affect here. So we can write JP J omega G and plus J PD J omega G and plus JPI J omega G. So we can write this expression, and from this we can write 180-degree. Since we are having two poles for the aircraft control system, we had CP of S for the unity inertia. I mean, we have already assumed. Okay, let me write first. IS square. This is the system, and since we are assuming I, the inertia is 1, so it will be 1 upon S square for I equal to 1. Inertia is 1. And for if you are having pole at origin, so the phase will be minus 180 degree, 90 degree for each pole. So, and for PD, we can write as it is GPD, J omega Z. And P I already have assumed it is giving the phase lag by minus 5 degree. So we can write minus 5 degree. So from this, we can write, from this expression, we can write the total phase in PD controller. We can write GPD, J omega Z. We can write PMP plus 5 degree. Or we can write, this is already you have 45 degree, that is already you have assumed, 45 degree. There's a 45 degree here. So we can write 45 degree plus 5 degree, this is 50 degree. Now, from the PD controller structure, we can come up with again the phase of the itself, the PD controller. So from PD controller, not at gain cost of frequency for any other frequency, you can thus, for the simple PD control system, let's see what are the gain, out of the phase of the PD controller. So PD controller, we know GPD is equal to KPD TS, we can write plus 1, or TPD you can write. So let me write T only. And the phase of the PD controller, we can write GPD J omega equal to tan inverse, we can write omega T. And if you notice here, here basically we have to assume the omega should be a positive value. For positive omega, the angle varies from of the PD controller 0 degree GPD J omega less than 90 degree for positive omega. This is easily calculate. Now we want to by this PD controller, we want to add some phase at the specified frequency omega c. So let's assume at some phase, because PD controller usually add the phase to the system, some phase divided by phi at a specified frequency by PD controller. And some frequency, let's denote as omega c. Okay. And so we can write from this equation, we can write phi is the total phase given by the PD controller equal to tan inverse at frequency omega c and into t. And from this expression, we can write tan phi equal to omega ct, or we can write t equal to tan phi divided by omega c. Now we'll find the time constant of the PD controller. So let me write the controller gain KPD can be chosen in such a way that to give desired gain crossover frequency. So for this purpose, the TPD, sorry, it is for this purpose, the PD controller design, we can write TPD from this expression equal to tan PMP, this you already have found, omega Z. So basically which can give the DGR, gain crossover frequency, for this particular PD controller. So you can write tan 50 degree divided by 0.12 equal to 9.93 second. So this is the time constant for the PD controller. Now we'll see the PI controller, which is basically giving the phase lag to the system. Now let's look. Now let's work on PI controller to find TPI. Here, let's assume the PID controller corner frequency to be sufficiently small. So let me look what is corner frequency, because TPI, the structure of TPI is, let me go back. So here I can write the structure of the controller transfer function of the, so what is the corner frequency for PI controller? GC PI, we can write KPI TPI S plus 1 by S. Or we can write, basically this expression we can write, if you divide both the proportional and integral part, we can write KPI equal to TPI plus 1 upon S. To find the time constant of the PI, because this is the basically, okay, let me, KPI TPI, you can take common, and 1 plus 1 upon TPI into S. So here, that's why you can find 1 by TPI actually, time constant, 1 by TPI actually, that basically the corner frequency, the system. So we can write 1 by TPI, let me write, equal to 0.1 omega Z. So what is this? Basically, what I'm assuming is, we are assuming the corner frequency to be sufficiently small so that the resulting PI phase lag does not have significant effect on the crossover region of the open loop response. So that's why we are choosing very small value of the gain crossover frequency. And as I said here, 1 by TP actually frequency and TI actually time constant here. After solving this expression, we can have TPI equal to 1 upon 0.1 omega Z, which is the solution of this 83.3 second. So now we have found the time constant for the PD controller, which is 9.93, and for PID controller we are having 83.3 seconds. Okay, now we'll find the total gain of the control system. Final part. To find the total gain at the gain crossover frequency, we can take the magnitude of the open loop transfer function equal to 1. So we can find at omega z equal to 0.12 radian per second, the open loop transfer function, open loop transfer function satisfy the following relation. I can write magnitude g naught of z omega z equal to 1. This is how we find the gain crossover frequency basically. And from this, if you substitute the open loop transfer function in this expression, we have k into gp j omega z into gpd j omega z gpi. Basically, these are the control part, and right, j omega z equal to 1. And from this expression, we can write k equal to 1 upon, we can write gp 0.12 j and gpd gc j 0.12 and gpi gc 0.j into 0.12. So from this, we can write further, if you substitute all the expression we have, k equal to 1 upon, for the plant, we can write 1 upon 0.12 square, and for the GCPD, we can write this 9.93 square, 0.12 square plus 1, and for the PI, we can write 83.3 square, 0.12 square plus 1 divided by 0.12. And from this, we can further solve it. We can write 0.12 cube and divide by 9.93 square, 0.12 square, 83.3 square, 0.12 square, and plus 1. And after solving this expression, the k comes out to be 1.105 into 10 to the power minus 4. And substituting this k in the expression for proportional integral derivative gains, what we have already found, substituting this expression k tpi tpd in this expression, we can find all the controller gains. Now, substituting k in the following controller gains, we find kpkd, kp equal to, we can write k into TPD plus TPI, which is 1.105 into 10 to the power minus 4, 9.93, 83.3. So the value yields to be 0.0103. And KD, KTPD, TPI, which is 1.105 into 10 to the power minus 4, 9.93 into 83.3, which yields to be 0.0915, yields to be equal to K, which is nothing but 1.105 into 10 to the power minus 4. And now we have all the parameters for PID controller at the controller gains. Now we can form the PID controller. The PID controller control law, we can write U equal to KP KDY dot plus KI 0 to T E tau D tau. We can write 0.0103 E 0.0915. This is Y dot plus 1.105 into 10 to the power minus 4, 0 to T, E tau, and D tau. Why it is Y dot? Because we are assuming the step reference signal, and for that R dot will be 0. E dot we can write R minus Y dot. So since we are assuming step signal, so R dot will be 0. So it will be minus Y dot. So this is how we can design the PID control for the aircraft system in frequency domain. But if you find from the simulation that the desired control system is not able to fulfill the mission objective, then what you can do is we can change the phase margin and increase the gain cost or frequency, and we can get our desired response. So this is how we design the PID control in using frequency domain in classical controls. Now we'll wind up the classical control design for the aircraft attitude control problem, and we'll move to our aircraft equation motion, how we can come up with the 6D of motion of the aircraft, and how we can come up the lateral and longitudinal motion of the aircraft, and how we can design the control system for those dynamical system. Thank you.